This chapter we are going to discuss acids and bases and the reactions between the two. Typical acidic solutions you'll find would be the liquids in lemons and lime. So lemon juice and lime juice taste acidic. So let's go through and talk about acids and bases. What's an acid and what's a base? So the original definition that came with Arrhenius was that an acid has an excess of H plus ions. And basically, what are some of the common properties? They taste sour. If you have litmus paper, it'll turn pink, and it reacts with metals to produce hydrogen gas. So we saw this with zinc and HCl. This gave us hydrogen gas plus zinc chloride. Okay. It reacts with bases to yield water. This one's called an acid-base neutralization. So that would be acid-base neutralization. Form water and a salt. And then it reacts with carbonates. So I can react it with sodium carbonate. And what you're going to get is water and carbon dioxide. And it doesn't have to be just carbonate, it can be hydrogen carbonate, like as in baking soda with vinegar. Okay, so what about bases? A basic solution contains an excess of hydroxide ions. Okay, it tastes very bitter, it's slippery and soapy, so turns your litmus paper blue for base. Okay, and it neutralizes acids. All right, and if you think about it, remember how we talked about alkali metals? And alkali means base. Okay, so if you recall the reaction with sodium metal and water, you ended up getting hydrogen gas plus sodium hydroxide. And it's this creation of hydroxide ions that makes your solution basic. Hence, that's why they're called alkali metals. Now, they show a jar with ammonia. Now, when we talk about bases, remember bases, the Arrhenius definition was to give excess hydroxide. But ammonia is a weak base. So it will, when you have ammonia in water, it will turn your litmus paper blue. So how can we come up with a definition of bases that allows us to account for some unusual ones? Well, ammonia is not that unusual. It's a very common reagent, but ones that don't clearly have a hydroxide. And so we now get to a much broader definition, and that's the Bronsted-Lowry definition of acids and bases. So the Bronsted-Lowry definition is the acid is a proton donor and the base is a proton acceptor. And this looks very similar to the Arrhenius definition, but by having a donor and acceptor, what this requires is that you need an acid-base reaction. Because you need to know what is the donor and what is the acceptor. And in this case, the base is the water. It accepted the proton, the H plus, to become the hydronium ion. Okay, and that's a hydrated H plus. So sometimes when we write hydronium, we equilibrate it back and forth between hydronium or just H plus. Because we have to have a reaction, we now can look at a reaction and say, listen, if my base here accepts a proton, then if I wrote this reaction in reverse, this can give up a proton. So this is called a conjugate acid-base pair. Likewise, if my water acts as an acid, then it gave up an H+, which means it forms a hydroxide. But if I went in reverse, reacting these two, then this is going to act as a base. So this too is a conjugate acid-base pair. So when you look at a conjugate acid-base pair, so here you're looking for the conjugate acid, you're going to look on this side. But when I give you a substance, let's say water, and I want the conjugate base, what that means is this is acting as an acid. So the conjugate base, you've lost an H+. So minus H+, which means that my conjugate base would be OH-. What happens if I ask for a conjugate acid? If I'm looking for the conjugate acid, then this must act as a base. And remember, a base accepted an H+. So what I get is that since the conjugate base, I lost one, I'm going to go in this direction. I'm going to gain an H+. And so you get the hydronium ion. Okay, so given that I'm looking for identify the base and the conjugate acid, so the base then here is which substance accepted a proton. So when I ask this, what I'm saying is which of my reactants, because I want to look for the base, not the conjugate, but the base. So which of my reactants accepted H+? Okay, so if this one accepted an H+, then it would be H3PO4. Well, I don't see it here, so that can't be it. If this accepts an H+, then I would get H3O+. Oh, it's right here. So the base is going to be water. Okay. What about the conjugate acid? Well, there's my conjugate acid. This is related to that. So when we're looking at the conjugates, you're going to be looking at the right-hand side. This is an arrow. The right-hand side of my arrow. When I just ask what's my base or my acid, you're going to be looking at the reactants. So since I'm looking for the conjugate acid, and I've identified my base, it's going to be the hydronium ion. All right, let's talk about the last set of definitions. So Arrhenius was the tightest. It was just H+ and hydroxide ion. Then we get to Bronsted-Lowry, which is a little broader. It's whatever accepts a proton is my base, whatever donates a proton is my acid. Now with the Lewis acid and bases, okay, this is the broadest, most general definition. The Lewis acid, bear in mind, is an electron pair donor. The Lewis acceptor, and the Lewis base is the electron pair donor. So Lewis acid, acceptor, acid. Okay, so here the H+ accepts this lone pair. Therefore, this is the acid. This donated this lone pair to form a bond. Therefore, it is a base. Okay, but now the reason that this is so significant is look at this substance. This reaction it's not a proton donor, but the boron can accept a lone pair of electrons to form a bond. When it does that, boron has an octet, the nitrogen still has an octet. This is a Lewis acid base reaction because I have an acid here. This is my Lewis acid, accepts a pair of of electrons, and my base is the one that donates the pair of electrons. All right, so here's your summary, this being the most specific, and this being the most general. Okay, when we talk about acids and bases, we'll be talking about using these two definitions primarily. When we go on to Lewis, we still use Lewis. Don't forget that we still use the Lewis acid base definition. But let's focus on Arrhenius and Bronsted-Lowry first. These are some of the reactions of acids. So we said acids react with metals and you form hydrogen gas. So when you have a metal container that contains acid, oftentimes it says corrosive. So why are acids corrosive? Because really it starts reacting with the metals in its container and the container begins to corrode. Okay? So what about with bases? This is called a neutralization reaction. Okay? And what we want to do is we don't want excess acid, we don't want excess base, we just want it to be neutral. I have water and I have calcium chloride. Okay, so when you react acids with metals, and we went through the activity series already, we know we're going to form hydrogen gas and salt, as long as the metal's more reactive than hydrogen. If we have acids and bases, you're going to form salts and water. Okay, and finally with your metal oxides. So basically, in the lab where we did calcium oxide, okay, and hydrochloric acid, this will react. You're going to form sodium chloride and you're going to form water. And this is when we see the metal oxides, oftentimes you're going to see it with your alkaline earth metals, because we normally don't find them plain, but we'll see them as oxides, and they do react with water, okay, or acids, and then you'll get water. All right. And finally, with the carbonates, we talked about this. You're going to get water and carbon dioxide. All right. Here, what about the salts that are produced? So when you have acid-base reactions, you always form water and a salt. Okay. And the salt is just basically, when you look at this double displacement, the other cation and the other anion. All right. And as you know, they're ionic compounds. We talked about the solubility of this one. We know with sodium cations is always soluble. All right. And remember, salts have a high melting point when they are a solid. So when we look at this reaction, which salt forms in the reaction of aluminum oxide and hydrobromic acid? So I form water and aluminum bromide. So this is my salt. These are all nonmetals. It's water. This is a molecular compound, right? So aluminum bromide right there. Okay. Now, when we talk about salts and water, okay, and acids and water, then we need to talk about electrolytes and non-electrolytes. So just recall our solubility tables. They're related but not the same. What is an electrolyte? So when they are dissolved in water, these are the compounds that can conduct electricity. And non-electrolytes, when they're dissolved in water, cannot conduct electricity. And that's the difference. So when I look at just pure water, I can't conduct electricity, so this light bulb doesn't go on. If I do sugar water, there's sugar in here. It's dissolved, you can't see it, but it doesn't conduct electricity either. So sugar is a non-electrolyte. If I use something like sodium chloride, I put the salt in solution, I dissolve it, then what happens is the ions can move in the water. I have charged particles, my ions, floating around in water, and because of that, that allows the electricity to flow through, and I can light up my light bulb. Okay, so let's talk about what are some types of compounds that are electrolytes and what are not non-electrolytes. So when we take a look, when you're looking at a metal wire, like a copper wire, okay, it's the movement of electrons in the wire that conducts electricity. But in your solution, in an aqueous solution, there aren't any free electrons moving around. But when you have an ionic compound dissolved in water, then it's the ion movement. So for instance, if I have sodium chloride, in water, in my sodium chloride solution, I have movement of my sodium ions and my chloride ions that allows the electricity to be conducted through my solution. Okay, so when we look at the types of electrolytes, we have acids, bases, and salts. So here, these are some of the acids, and this is an acid. Here I have strong bases and I have a weak base, ammonia. And here I have my salts. So remember, they have to be soluble. Okay, so a solid at the bottom of your flask is going to conduct electricity because they don't have ions in solution. So like, let's say calcium phosphate. But here, as long as they're soluble, they can conduct electricity because you form ions. So ions are formed. Okay, so you need to make sure that you have ions that are being formed. Here, these are all molecular compounds. And remember, there are no ions. So when they dissolve in water, they're on the molecular level. We still can't see it because it's on the molecular level, but there are no ions formed. So therefore, these are non-electrolytes. They cannot conduct electricity because they don't form ions. Okay, so in this one, which will not dissociate in water, this is an acid, so you form H plus and Cl minus. This is a salt, you form K plus, Br minus. Here's my strong base, sodium hydroxide, you form Na plus, OH minus. This one is molecular. So no ions are formed. So it can dissolve in water so that basically, here's my water. I have little methanol molecules floating around, but the methanol doesn't dissociate. Here, if I put in HCl, here's my water, then my HCl would be H plus floating around, Cl minus floating around. Okay, so that's the difference. So remember, when we dissociate, when this is dissolved with water, then we're going to form aqueous solution, and it's the ions that you're going to see. That's what actually happens. What happens also is, why does it do that? So remember, when my ions separate, they're surrounded by water. So all these oxygens on the water is like, ooh, we love you, sodium ion. All the hydrogens around the water, because they're slightly positive, surround the chloride ion. Oh, we love you, chloride. So the sodium and the chloride have a bunch of groupies here in their water, and so they're happy with that. And they don't have to go back and form the solid. Okay? So these are called ion dipole interactions. So what about this ionization? It's just the process of forming the ions in solution. Okay? So acids ionize in water. So if I bubble hydrogen chloride through water, then the process of it is it's going to ionize to give you the hydronium ion and the chloride ion. Okay, likewise with your other acids. Bases too will ionize. So if I had bubbled ammonia, get aqueous ammonia in there, I'll form my hydroxide ion and the ammonium ion. Okay, now what's the difference between strong electrolytes and weak electrolytes? So you ran your current through a solution with a strong electrolyte, your light bulb will be very bright. If you run it through a solution with a weak electrolyte, your light bulb will be very dim, like the battery's dying. But there's a more quantitative definition for it, and that is strong electrolytes undergo complete ionization in water. What that means is if I said I had 2 molecules of hydrogen chloride and I bubble it through water, then at the end I don't have any more molecules of hydrogen chloride in my water. I'm going to have 2 H pluses and 2 chlorides, and you won't see HCl in there. Okay, this has been completely dissociated. When I have a weak electrolyte, let's say like acetic acid, and I put in like, let's say 5 molecules of acetic acid, then what you may see, is 1 will dissociate, so I have my acetate, but the remainder stay as acetic acid in the molecular form. So it doesn't, not all of it dissociates. Actually, a very small portion will dissociate. Okay, so everything here. So in this example I'm giving you, only 1 of the 5 acetic acid molecules dissociated. So it's an incomplete dissociation, which is very different than the hydrogen chloride or hydrochloric acid, where put it in water and all of it comes apart. Okay. So when we look at strong and weak electrolytes, my strong acids and my strong bases are strong electrolytes. Okay, and the weak acids and weak bases are weak electrolytes. So hence why we call them strong. Strong acids, strong bases, strong electrolytes. So these are all strong acids. These are all strong bases. And then any of the soluble salts, all right, are strong electrolytes. So salts that are soluble, strong acids, strong bases. On this side, weak acids, weak bases are weak electrolytes. Okay? Now salts can dissociate into more than 2 ions. So here, sodium chloride produces actually 2 molar of ions. But here, calcium chloride, when this dissolves, I get 1 calcium ion, but I get 2 chloride ions. So in sum, I get a total of 3 moles or 3 molar of ions. Okay? So here, we want the concentration of bromide ion in magnesium bromide. Well, when magnesium bromide dissolves, okay, then we get the magnesium ion plus 2 bromide ions. If this was 1.5 molar, then basically it's a 2 to 1. So 1.5 molar magnesium bromide. And we know for every 1 magnesium bromide, we get 2 bromide ions. So the concentration is going to be 3.0 molar bromide ion. Okay, so it would be C. Now, if you're asked for the total, then you would calculate the magnesium as well and add them together. Okay, water. Water is a very unique substance, and when you look at a glass of water, it basically not only has just the molecules, but it has some hydronium ion and some hydroxide ion. Not a lot. You're drinking something that's safe for you and good for you. But what we do is we call this self-ionization when this water acts like a base and accepts a proton and becomes a hydronium ion. And this water acts like an acid and it donates the proton and becomes hydroxide ion. And this process is called auto-ionization. Okay, turns out when we look at it, see how it's 1-to-1, the concentration of hydronium ion, let me just erase my writing here, the concentration of hydronium ion is equal to the concentration of hydroxide ion. And you can see that in both cases, at 25 degrees Celsius, the concentration is 1 times 10 to the minus 7th molar. Now this is like less than 1 in a million. This is like 1 in 10 million. But there is still some present. Okay? When you multiply the two, you get 1 times 10 to the minus 14. This is called the equilibrium constant for water. Okay? What happens though is when I have an acidic solution, my hydronium ion concentration is greater than my hydroxide. When it's basic, my hydroxide is greater than hydronium ion. Remember, those two concentrations, whenever you multiply them together, has to equal 1 times 10 to the minus 14. Now, instead of working with a lot of different exponents and tiny exponents or large exponents, what we do is we introduce the concept of pH. And by definition, here's your formula. The pH of a solution is equal to the negative log of the hydronium ion concentration. So in pure water, at 25 degrees Celsius, the hydronium ion concentration is 1 times 10 to the minus 7th. We take the negative logarithm of this, we get 7, which means this is the neutral point. So when my pH is greater than 7, it's going to be basic. When my pH is less than 7, it's going to be acidic. So here's just a list of the ranges. So if my hydronium ion concentration is really, really small, then you can see the pH is really large. If my hydronium ion concentration is large, then you can see that my pH is small. Some typical values of common solutions. Household ammonia is at 11. Bleach is going to be way up here. Okay. Your stomach juices is a pH 1. Orange juice, lemon juice, you can see how acidic your juices are. And even your coffee. And blood is ever so slightly basic. So when we say by what factor, that means how many you're going to multiply, how many times. So when we solve this, pH 5 and pH 3, the hydronium ion let me just rewrite this a little. pH is equal to minus log of my hydronium ion. So if I rewrite this, negative pH is equal to the log of hydronium ion. Raise both sides to the power of 10. 10 to the log of this is equal to the hydronium ion concentration. And that's equal to 10 to the negative pH. So just be aware, this is, if I'm given the pH, I can get my hydronium ion concentration. If I'm given my hydronium ion concentration, I can get pH. So these two are related. In this case, what we're going to do is we're going to solve for the hydronium ion concentration at pH 5 and at pH 3, and then divide the two. So let's do it. So at pH equals 3, the hydronium ion concentration is going to be equal to 10 to the negative 3. Okay? And at pH equal to 5, the hydronium ion concentration is equal to 10 to the minus 5. So when we say what's factor the solution of this more acidic than pH 5, so we'll say 10 to the minus 3 divided by 10 to the minus 5. Okay? And what does that give us? That gives us 10 to the 2, or equal to 100. So it's 100 times more acidic than a solution of pH equal to 5. All right, so now we know how to use both of these formulas. Okay, so when would you look at this? If it's 1 here, then the pH is 5. If it's 2 here, it's slightly less. This is just so you can get a feeling for how pH works. Okay, so when we calculate the pH of a 0.015 molar solution, so we know pH is equal to minus log of my hydronium ion concentration. So minus log, this is base 10, 0.015, and what we get is 1.82. Okay, now one thing about exponents, if this is two significant figures in your exponent, you're going to look after your decimal point. What about looking at 0.02 molar hydrochloric acid? So the pH is equal to minus log of my hydronium ion concentration, which is equal to minus log of 0.020 molar. Okay. Which is 1.69897. Now we have to figure out the number of significant figures. This is two significant figures, so we look after the decimal point and we have two significant figures there. So this is going to be equal to 1.70. That's a significant 0 here. So 1.70. Okay, now this takes 2 steps. So we're not given the H plus concentration, we're given the hydroxide concentration. So we have to go back. Remember how we know that the hydronium ion concentration times my hydroxide concentration is equal to 1 times 10 to the minus 14? Okay, so we're going to have to use this equation to get the hydronium ion concentration, and then we can calculate our pH. Okay, So step 1, we'll use this equation. Step 2, we'll use that equation. So step 1. We're looking for the hydronium ion concentration. And that's going to be equal to hydronium ion times my negative 2.5 times 10 to the negative 11 molar. And that's equal to 1 times 10 to the minus 14. So we'll divide both sides by my 2.5 times 10 to the minus 11. And my hydronium ion will therefore be equal to 4.0 times 10 to the negative 234. Okay, molar. So we finished this one. Now we need to get the pH. So the pH minus log of 4 times 10 to the minus 4. That's going to be equal to 3.3979. Now, how many significant figures? In a normal number, that's 4. But the log value, the 4.0, that's 2 significant figures. Once I get my log value, I need to look at after the decimal point. Okay, so our pH is going to be 3.40. Okay, should be this one, but this needs a 0 at the end. All right, let's talk about the reactions. Now that we know how to do calculations to talk about acidic and basic solutions, let's talk about the reactions. An acid and base reaction, neutralization in fact, will give me salt and water at the very end. But what's important to learn now is how to write an overall ionic equation and a net ionic equation. So what do we call this top one? Everything's written in neutral form. So this is like the balance equation is what we call them, even though they're formula units, the molecular equation. Everything is neutral and in their molecular or formula unit form. Now, what we do with the overall ionic equation is we all ionic compounds that are aqueous, we take apart to its component ions. Okay, so in this case, we look at HCl. Oh, H plus, Cl minus. Okay, we take a look at sodium hydroxide. And this is, again, where all those polyatomic, knowledge of your polyatomic ions comes in. Because instead of breaking up the O and H separately, remember, this is hydroxide. This is a single unit. And now, because we're putting down all our ions, it's not neutral, we need to put the charges. Here, breaks apart. But see, this isn't aqueous. This is not aqueous. This is a liquid. So we don't touch it. We just carry it down. Okay? So basically, anything that's not aqueous and ionic that can, or a strong electrolyte, you're just going to copy down. So from here, strong electrolyte, strong electrolyte, strong electrolyte, non-electrolyte. So we don't touch this. That's why it comes down. Everything else that's a strong electrolyte we take out into its component ions. Now, what do we do with all this? Well, what we need to do with all this is we need to figure out what is exactly the same on the product side and the reactant side. Anything that's not involved in the reaction, any ion not involved in the reaction is called a spectator ion. Okay, so what we do is we take a look. So here you can see the chloride here is exactly the same. Chloride, negative charge, aqueous. That's a spectator ion. The sodium ion, same here. What happened to H+? It became part of my molecule of water. What happened to hydroxide? It became part of my molecule of water. So in the net ionic equation, we remove all the spectator ions. So don't use this, don't use that. Now you can say H+, OH- goes to water. And that's my net ionic equation. What really happened here? Now, when you get to your net ionic equation, make sure you are at your lowest, right, whole number ratios after you finish removing your spectator ions, whole number ratios. Just like when we were taking a look at our molecular equations and balancing them, we had to make sure they had the lowest whole number ratios that made them balance. You're going to do the same with your net ionic equation. Okay, now titration. So titration is an experiment where you have a standard concentration for one reagent and the other reagent you don't know the concentration, you just know the volume. And when you do the reaction, you're going to stop just where everything has been completely reacted, and then you can determine the concentration of your unknown reaction. Okay, so if we had a base or acid present and we didn't know the concentration, if we do an acid-base titration, we can determine the concentration. How do you know when to stop? We use what we call indicators. They change color in the range of pH of interest. Okay, so for us, we normally use phenolphthalein. And what happens with phenolphthalein is that it's colorless under acidic condition, and then at the end point it's a very light pink, you can barely tell. If you continue to go past that, so it's basic, it turns a very dark pink. So just at the end point where you see very faint pink, then you stop. And you can tell me the volume of base you used and determine the unknown acid. So let's take a look. We're doing sodium hydroxide, it's AQ, plus hydrochloric acid, AQ, goes to water and sodium chloride. Now, why do we need a balanced reaction if we're only focusing on my two reactants? Because remember, you need to know what your mole to mole ratio is. So if you don't have it balanced, you may not have the correct mole to mole ratio. So you're titrating sodium hydroxide, so you want the concentration of the sodium hydroxide. So let's start there. We need the concentration of sodium hydroxide, and that's going to be equal to the moles of sodium hydroxide divided by the volume in liters. Okay? Well, we have the volume. We can convert that. It's right here. But I don't have the moles of sodium hydroxide. How can I get that? Because I know this part, the equation. So now I can say, well, from the moles, if I want the moles of sodium hydroxide, I may be able to get that by knowing the moles of hydrochloric acid. But I'm not given the moles of hydrochloric acid. I'm given concentration and volume. But I know from concentration and volume, I can get the moles of hydrochloric acid. Okay, so we're working backwards, but now we know the steps we need to take. First, I need to get the moles of hydrochloric acid. Second, I need to convert with my mole-to-mole ratio, which so turns out to be 1:1, the moles of hydrochloric acid to moles of sodium hydroxide. And third, now I can get the concentration of my sodium hydroxide. Now notice you're using this molarity equation twice. Make sure you know what step you're on so you know what values to use. Okay, and we know this is 1:1. Okay, so let me just go ahead and make some space and let's do step 1. Step 1. So we know the concentration of hydrochloric acid is equal to the moles of hydrochloric acid divided by the volume of the hydrochloric acid in liters. So the moles of hydrochloric acid is equal to the concentration times the volume. Okay, so we can just do this. And just go ahead and plug everything in. Just go ahead and make some space here. We know it's 0.1096 moles per liter. I need some more space here. So hydrochloric acid times the volume, and so I'm going to convert that to liters. 0.2259 liters. Okay, so for the moles of hydrochloric acid, we know it's 0.1096 times 0.02259. And I get 4 significant figures, 2.476 times 10 to the minus 3 moles of hydrochloric acid. Okay, so that part's done. Now, for step 2, we needed to do our mole-to-mole. And the good part is it's 1:1. So 2.4, this is step 2, 76 times 10 to the minus 3 moles of hydrochloric acid. And we know from our balance equation that for every 1 mole of hydrochloric acid, we needed 1 mole or used 1 mole of sodium hydroxide. So that gives us 2.476 times 10 to the minus 3 moles of sodium hydroxide. So, yay, step 2 is done. So I'm going to erase the work here. I finished step 1. We finished step 2. All we need to do now is get the concentration of sodium hydroxide. So let's do step 3. So for step 3, concentration of sodium hydroxide is going to be equal to the moles of sodium hydroxide, 2.476 times 10 to the minus 3 moles, divided by, and the volume I'm going to convert to liters, 0.2500. Notice there's 4 significant figures, and what we get is 0.09904 molar sodium hydroxide solution. Okay, so you're done. Now sometimes you'll see us talk about using this equation, which is much easier, but you have to be aware that it only works for specific cases. Okay, so only if the mole to mole ratio between acid and base is 1 to 1. If not, you cannot use this. This is essential. Okay, only if mole to mole ratio between the acid and base is 1 to 1, like what we saw with hydrochloric acid and sodium hydroxide. Then you can use the equation. The concentration of acid times the volume of acid is equal to the concentration of base times the volume of base. And if we do use this equation, we're looking for the concentration of base. That's going to be equal to 0.1096 molar times my 22.59 milliliters divided by the 25 milliliters. And that gives us 0.09904 molar sodium hydroxide. Okay, so you can use this equation, but you must satisfy this condition, 1 to 1. Okay, all right. So what is the molarity of a sodium hydroxide solution if 21.93 milliliters of base is required to titrate 0.243 grams of oxalic acid? So, 1, we need an equation. We need a balanced chemical equation. Before we can do anything. And then 2, since the equation is going to be giving our relationship, okay, in moles, we need to convert everything into moles. All right, so this is a double displacement, acid-base neutralization, okay, and this is aqueous. I need 2 here because I have 2 of those, 2 there. Okay, so now that I have the relationship, I know I can't use that equation I told you because I no longer have a 1 to 1. So let's work through and figure out what are the steps we need to do. Now that we have our balanced equation, we need the moles So we need to convert mass to moles. Okay, of my oxalic acid. And then I need to go from moles of oxalic acid to moles of sodium hydroxide, and with the volume now, and then use the formula to get the concentration. So the concentration is going to be equal to moles of sodium hydroxide divided by the volume in liters. Okay, so let's go ahead and get some of the information we need. So for oxalic acid, the molar mass of oxalic acid because this is a solid, so I'm given actually the mass of it, of oxalic acid, is equal to, so it's 2 oxygens, right? 2 carbons, 2 oxygens, 2 carbons. Okay, and then 4 oxygen. So I get something like 90.038 grams per mole. Okay. And I'm just going to go ahead and draw a line here. I'm just going to have a small space to work with. Okay. So, number 2, 0.243 grams of my oxalic acid and I know it's 90.038 grams per mole, and that gives us 0.243 divided by 90.038. I get 0.002699, and this is 3/6 figs, but I'm not going to round yet, moles of oxalic acid. Okay, so we're done with step 2. Okay, now before I erase the equation so I can get some space to work with, what is my mole to mole ratio here? So 1 mole of oxalic acid for every 2 moles of sodium hydroxide. So let's go ahead and get our moles of sodium hydroxide. So for the next step, I have 0.002699 moles of oxalic acid. And my mole to mole ratio is I have 2 moles of sodium hydroxide for every 1 mole of oxalic acid. And when I calculate that out, I get 5.398, again, 3/6 figs, times 10 to the minus 123 moles of sodium hydroxide. All right, so now we've finished step 3. So now we can move on to step 4. I have my moles of sodium hydroxide, and I need to just convert my volume to liters. Okay. Let's go ahead and finish step 4. Concentration of sodium hydroxide is going to be equal to the 5.398 times 10 to the minus 3 moles of sodium hydroxide. Divide this by, that's 3 sig figs. That's 21.93 milliliters. So when we convert 0.02193 liters of solution. So for our answer, .02193, okay, we get 0.246 molar sodium hydroxide solution. And that's in 3 significant figures because of the top value, the moles. And there you have it. So the big part for doing these problems then is just making sure you map out your steps one by one so you know exactly what to pursue as you do your calculations, and keep it organized. It's hard on a single slide. That's why I apologize for all the erasing, but I've tried to number each step so you know I'm doing step 1, I'm doing step 2, I'm doing step 3, so you know exactly where you are. Okay, let me erase this so you can see what's been typed. Okay, all right, so we did all the calculations, and it just shows you what the solution map is. All right, so now let's do one more problem. All right, we are doing nitric acid. What does this nitric acid look like? HNO3. All right, now let's go ahead and take a look. So if I do HNO3 plus NaOH, we get a salt and water. But it's balanced. This is 1:1. So since my mole to mole ratio is 1:1, let's try that other equation I gave you. We're going to use MAVA is equal to MBVB. Okay, and we're looking for MA. So MA is equal to MB VB over V8. Now, like I say, you need to be careful and make sure this condition is met. So even if you're in a hurry, make sure you think about this before you just resort to this equation. All right, so the concentration of base is 0.20 molar. The volume was 3.6 milliliters. And then here I used 10 milliliters of nitric acid. So when I go ahead and calculate it out, 0.2 times 3.6 divided by 10, I get 0.072 molar. And there you go. So once again, just be very, very careful. Think about your conditions before you can use this. This equation isn't general. It's only if your acid-base neutralization has a 1:1 relationship between your two reactants. Okay, so we talked a little bit about the total ionic and the net ionic equations. Remember, whenever we were having a strong electrolyte, we have to take them apart into their component ions. So again, knowing all your polyatomic ions is essential to do this. Okay, when you have weak electrolytes, then or non-electrolytes, you just keep them as molecules. All right, so this is a non-electrolyte. and this is a weak electrolyte. And when we write them, we don't break them apart. Okay? So, and then anything that's not aqueous, solid, liquid, or gas, we just write as is. Okay? Okay? So, and the net does not include the spectator, but we need to get to the total ionic, identify the spectator, and then write the net ionic. Make sure that's balanced, the lowest whole number ratios across the coefficients, and it's balanced both by charge and substances. All right, so let's write the net ionic equation for the following. So these are the things you need to think about. This is an ionic compound, soluble. It's a strong electrolyte, so we take it apart. This one, it's soluble, it's ionic, it's a strong electrolyte. Take it apart. This one is a solid, so we just copy it. And then finally, this one, sodium chloride, is a salt, soluble, so we take it apart because it's a strong electrolyte. So now when we go through and write the total ionic, so let's write the total first. You have your barium. Okay. Now what about this? Listen, this does not exist. You know from all the semester, you know that chloride exists as this. So why do we have the subscript? To make it neutral, we needed two of them to make this compound neutral. And that's because we know the chloride is just Cl minus, this 2 becomes my coefficient, because that's what it means. I had a barium ion, and I needed 2 chloride ions. And now this is neutral. Okay? So that subscript is to tell us I have 2 chlorides. Now let's take a look at the next one. The next one, sodium ion, exists like that. There's no such thing as Na2 plus. No, 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 no. Don't even think it. So, what's the subscript 2 for? To tell me I needed 2 of them. But look at sulfate. When you know your polyatomics, you know this ion here is my sulfate ion. So don't separate it into its atoms. This is my unit. It has 4 oxygens, 1 sulfur, and it has a -2 charge. Now on the product side, I have my barium sulfate. It's a solid, so I just copied down. I didn't do anything with it. And here I have 2 sodium chlorides. So that means I have 2 sodium ions and 2 chloride ions. Now that I have my total ionic equation, let's identify the spectator ions. Now remember, spectator ions are those ions that float around in solution. They're not part of the reaction. They just go, react. I'm going to watch. Now you will see that in solution, what happens is that they aren't part of it. Their state is exactly the same on the reactant side and on the product side. So my chloride ion is a spectator. See how they look exactly the same? Oh, look it. This looks exactly the same too. So these are my spectator ions. Why am I crossing them out? On the total ionic, you leave it, but in the net ionic, we remove them. So in the net ionic equation, Now that I have removed my spectators, and I'll write it up here at the top, it looks like this. The barium ion okay, take care of that, plus the sulfate ion, take care of that, gives me a solid. And this is my net ionic equation. Okay? Let's do another practice. So in this one, this is balanced, okay? If you're given an equation that's not balanced, you have to balance your molecular equation first before you do the rest. So here's my molecular. So again, what we're going to do is we're going to identify those ionic compounds that we need to dissociate because they're strong electrolytes. This is ionic, it's soluble, it's a strong electrolyte. It's a strong acid, strong electrolyte. Oh, that's a gas. I'm not going to touch it. Oh, sodium chloride, ionic compound, strong electrolyte. Take it apart. Water. Oh, here it is. Give me a different color here. Don't take apart carbon dioxide. Don't take apart water because look at it. It's not aqueous. It's a liquid and it's a gas. Okay. So now let's do our total ionic. 2 sodium ions plus my carbonate. Okay. So notice how the 3 stays as a subscript because that's part of my polyatomic ion. The 2 became my coefficient because the sodium ions look like this, Na+. And the 2 tells me I need 2 of them to make this neutral. When it's a coefficient, it applies to each one. When it's a subscript, it only applies to the element before it. So I have 2H+, 2 chlorides. Okay. Then on the product side, the CO2, it's a gas. I'm not going to touch it. I just copy it down. Sodium chloride is a strong electrolyte. And again, that coefficient applies to both. So 2 sodium ions, 2 chloride ions. And look it, this is a liquid, so it's water. Don't touch it. All right. Now, what are my spectator ions? So my spectator ions, look at how the sodium right here looks just like that. Okay. Notice carbonate, carbon dioxide is different. H+ water is different. Oh, this one looks exactly the same. Those are my spectator ions. They're not part of the reaction. Now we can write the rest of our equation. So it turns out if we take carbonate and it reacts with acid, it forms carbon dioxide gas and water. Okay, and there you have it. All right, this is all my coefficients are the lowest whole number ratios. All right, so what about this one? The net ionic equation when hydrobromic acid reacts with potassium hydroxide. So let's write that down. Hydrobromic acid reacts with potassium hydroxide. Okay, that's a Q, right? And when I do my double displacement, it gives me water and then a salt. This is aqueous and this is a liquid. Okay, so now if I do my total ionic equation, So I'll put that in purple. Strong acid, H plus Br minus. There's my strong base, K plus hydroxide goes to water. That's a liquid, so don't touch it, just copy it down. And then KBr is a strong electrolyte, it's salt and water, right? Ionic compound in water. Okay, so now all we're going to do is I'm going to cross out things that are exactly the same on the reactant side and the product side. So Br minus, that's the spectator. K plus, that's the spectator. So when I write down the remainder, I have H plus OH minus. That gives me water. So H plus hydroxide, water. Okay, so that's what we do. And basically, just so you know, for any acid base, our typical Bronsted-Lowry Arrhenius acid base neutralization, well, we said it gives you salt and water. And typically, this is going to be the net ionic equation for that acid base neutralizations. The net ionic equation, acid base neutral. So acid base neutralization. Okay, and we're done now with the last chapter.